Hello, my name is Hyun Yoon. Today, I'm going to talk about the numerical simulation and weather forecasting. Numerical simulation was one of the core concepts in this course. It involves using mathematical models and computer programs to simulate how real-world systems behave over time. Instead of solving complex equations by hand, we use computers to approximate the results. These simulations rely on input data and follow mathematical rules to predict how a system will evolve, like changes in weather, temperature, or pressure. This approach makes it possible to analyze systems that would otherwise be too complex to study accurately. From this course, I studied how to apply numerical methods to approximate solutions to mathematical problems, and I also learned how to use computational tools such as Python to use those numerical methods. And also I learned to visualize the simulation results by using Matplotlib, for example. And we also learned how parallel computing helps speed up simulations by dividing tasks across multiple processors, which is very important in large-scale simulations like weather prediction. And also I want to discuss why I chose this topic. I chose weather forecasting as my topic for this presentation because it is a direct application of what we learned in class, as it uses computational math to solve real problems, and it runs on parallel computing systems due to the massive amount of data. And finally, it provides the visual outputs that help scientists and the public, such as us, to understand and act on the forecast data. Now I will talk about the background information that is related to this topic. Weather forecasting is a great real-world example of numerical simulation, and it is also called as numerical weather prediction. In this process, we use mathematical equations to simulate how the atmosphere behaves over time. Some of the most important equations include the Navier-Stokes equations, which describe how air moves like a fluid, and the thermodynamic energy equation, which models changes in temperature. We also include equations that track moisture and humidity, so we know how water vapor moves and condenses into clouds or rain. Now I'll explain how NWP works. To simulate the weather, scientists first divide the atmosphere into a massive 3D grid made up of thousands or even millions of small cubes. At each grid point, the computer calculates key variables such as temperature, pressure, wind speed, and humidity. These values are updated repeatedly using numerical methods that approximate how the atmosphere changes over time. The process begins with initial conditions, which are the real-world data collected from satellites, weather stations, and weather balloons. The model then steps forward in small time intervals and predicts how the entire system evolves. By repeating this process, the simulation builds a forecast of future weather, hour by hour and day by day. The more grid points and the time steps we use, the more accurate the forecast becomes, but it also requires more computing power. Now I'll explain why supercomputers are needed. First, weather simulations involve a massive number of calculations. To get accurate forecasts, we need to model the entire atmosphere with high-resolution 3D grids, as I mentioned before. At each point, the grid calculates temperature, pressure, wind, and repeats this process every few seconds to predict how the weather changes over time. This quickly becomes a huge computational task that is far beyond what a normal computer can handle. That is why weather forecasting depends on supercomputers, which use parallel computing to divide the workload. Instead of one processor doing all the calculations in order, thousands of processors work at the same time. This allows scientists to produce forecasts fast enough to be useful. For example, predicting a hurricane landfall days in advance. After the simulation is complete, it generates huge amounts of raw data, including numbers of representing temperature, pressure, wind speed, and more at every grid point. But raw numbers aren't helpful on their own. That is where data visualization comes in. Scientists and forecasters use color maps, animations, and graphs to turn the simulation data into images that are easy to understand. For example, we can visualize rainfall intensity as heat maps, wind direction as arrows, hurricane paths as time-lapse trajectories. These visuals are what we see on the news, weather apps, and emergency broadcasts. Without visualization, even the most accurate simulation would be almost useless because people wouldn't be able to interpret the results quickly or clearly. Next, weather forecast connects directly to the core concepts that is discussed in this course. First, it uses computational mathematics to solve complex differential equations. In weather forecasting, these equations model how air moves, how heat transfers, and how moisture behaves in the atmosphere. Second, it applies numerical simulation, which we learned about using algorithms to approximate the behavior of physical systems over time. Second, it applies numerical simulation, which we learned about using algorithms to approximate the behavior of physical systems over time. The entire weather model is a simulation evolving over space and time. And finally, it uses big data visualization to turn complex simulation output into understandable graphics. Overall, weather forecasting is a perfect example of how everything we learn comes together in one real-world application. Now I'll explain in detail more about each applications in science and engineering. The first application is severe weather alerts. Weather systems like hurricanes and typhoons are extremely dangerous and can develop quickly. Using real-time atmospheric data from satellites and weather stations, numerical models simulate how these systems will evolve. By solving complex fluid dynamics and thermodynamic equations, scientists can estimate the path, intensity, and timing of extreme weather events. For example, simulations helped predict the path and storm surge of Hurricane Katrina by allowing the residents evacuate earlier. Similarly, Typhoon Haiyan was modeled days before landfall, allowing millions to be relocated. These simulations directly feed into public warning systems, giving people time to prepare and government times to respond, and ultimately saving lives and reducing economic losses. Without fast and accurate numerical simulation, many regions would face disasters with little or no warning. The second application is climate research, where scientists study how much Earth climate may change over decades or even centuries. These models are called global climate models, or GCMs, and they use the same physical equations we apply in weather forecasting, like the Navier-Stokes equations and thermodynamic energy equations, but over much longer timescales. Instead of predicting the weather next week, GCMs simulate how Earth's atmosphere, oceans, and land systems respond to changes like rising greenhouse gas levels, deforestation, or changes in solar energy. These simulations help us understand the potential impacts of climate change, including global temperature rise, melting polar ice, sea level rise, and increased frequency of extreme weather events like droughts, heat waves, and superstorms. The work of organizations like the Intergovernmental Panel on Climate Change is based on numerical simulations run by climate scientists around the world. Without these tools, we wouldn't be able to make informed policy decisions or prepare for the future of our planet. The third application is the aerospace engineering. Engineers use a power technique called computational fluid dynamics. It allows them to test and optimize design virtually without needing a wind tunnel or physical prototype right away. For aircraft, CFD simulations allow designers to optimize wing shapes for better lift and reduce drag, improving fuel efficiency and flight stability. In spacecraft engineering, simulations are used to model re-entry conditions where heat and pressure become extreme. Engineers use this data to design heat shields and ensure structural safety. CFD is also used in jet engines, helicopter blades, and drone design, helping engineers understand how different shapes behave under different airflow conditions. These simulations make aerospace design faster, safer, and more cost-effective, and they rely on the same computational math and physics we use in large-scale weather models. The fourth application is agriculture, where farmers rely on forecasts to make smart decisions about planting and harvesting. Numerical simulations provide detailed predictions about rainfall, temperature, and wind, which are all crucial for crop management. For example, knowing when rain is expected can help farmers plan irrigation schedules, which can save both water and energy. Forecasts also help determine the best planting windows, avoiding droughts, frost, or storms that could damage crops. These simulations contribute to higher yields, reduced crop loss, and better resource management, especially in regions where weather patterns are hard to predict. In the future, simulation-based agriculture will become even more accurate, which will then support global food security in the face of climate change. Final application is energy management, especially for renewable energy systems like solar and wind power. These energy sources depend on environmental conditions. For example, wind turbines only produce power when the wind is blowing, and solar panels need constant sunlight. Weather simulations help predict when and where these conditions will occur. If forecasts show that wind speeds will be low tomorrow, power grids can adjust by drawing energy from other sources or storing energy in advance. This helps maintain a stable electricity supply, prevents blackouts, and improves the overall efficiency of energy distribution. As more countries adopt renewable energy, water-based simulations will become even more essential in building smart, flexible, and clean power systems. To conclude, numerical simulation and weather forecasting is an incredible example of how computational science directly impacts the real world. It brings together the core concepts I studied, which includes numerical methods and data visualization, and applies them to challenges that affect millions of lives every day. Whether it is saving lives during storms, helping farmers grow food, designing safer aircraft, or making renewable energy more reliable, these simulations are essential to modern science and engineering. This project helped me see how what we learned in class isn't just theoretical. It is used to solve urgent global problems. And here's my citation. Thank you.